Life is based on water, primarily because of water's solvent properties. Understanding this and the other properties that make water so important means understanding water's molecular structure. Water is a solvent for many of the molecules in living organisms, primarily because it's a polar molecule. This means that electrons shared by the hydrogen and oxygen atoms are more attracted to the oxygen than to the hydrogen. This unequal attraction of electrons generates partial electric charges within the water molecule. The oxygen atom has a partial negative charge, and the hydrogen atoms have a partial positive charge. Therefore, a water molecule as a whole has positive and negative ends. The molecule is polar. When two liquid water molecules approach each other, the partially negative oxygen atom of one water molecule is attracted to the partially positive hydrogen atom of the other water molecule. Hydrogen bonds form between water molecules, causing them to stick together. These same hydrogen bonds form between water and other molecules that carry charges. Here's an example of how water acts as an efficient solvent of table salt or sodium chloride. Water molecules surround the sodium and chloride ions of salt. The oxygen atom in each water molecule, with its partial negative charge, bonds to a positively charged sodium ion. The hydrogen atoms of the water molecule, with their partial positive charges, bond to the negatively charged chloride ions. Water's polarity makes it an effective solvent for charged or polar solutes. The hydrogen bonds that form between water molecules are responsible for one of water's most unusual properties. Although solids are usually denser than liquids, water expands and becomes less dense as it changes from a liquid to a solid. This property allows ice to float on water. Let's examine why ice floats on water. In ice, each water molecule forms 4 hydrogen bonds with 4 adjacent water molecules, giving the ice an ordered lattice structure. In this structure, the hydrogen bonds overcome the motion of the individual water molecules, holding them in a fixed 3-dimensional pattern. In addition, the water molecules are spaced farther apart, making ice less dense than water. As ice melts, hydrogen bonds are broken, and the water molecules are free to move closer together, forming liquid water. Liquid water, therefore, is more compact or denser than ice. What would be the implications for life if ice were denser than liquid water? The hydrogen bonds between water molecules are also responsible for another unusual property of water. A great deal of heat energy is required to change water's phase or state from solid, ice, to liquid, or from liquid to gas, steam. Water has an extraordinarily high heat capacity, meaning that it can absorb a great deal of heat before it increases in temperature. Water's heat capacity is unusually high because it contains many hydrogen bonds. A large amount of energy is needed to break the hydrogen bonds between the molecules before the temperature of the water rises. Although liquid water is denser than ice, the molecules in liquid water move more freely. When liquid water has absorbed enough energy to break all of the hydrogen bonds, it changes from a liquid to a gas, steam. Sometimes a water molecule dissociates or breaks up, forming a positively charged hydrogen ion and a negatively charged hydroxide ion. In any sample of water, the fraction of water molecules that are dissociated is extremely small, so water molecules are much more common in the human body than are hydrogen and hydroxide ions. Substances called acids and bases influence the concentration of hydrogen ions in solutions. An acid, such as hydrochloric acid or HCl, releases hydrogen ions when placed in water. A base, such as sodium hydroxide or NaOH, produces hydroxide ions when placed in water. The hydroxide ions produced when NaOH dissociates reacts with hydrogen ions to form water molecules, and thus reduces the concentration of hydrogen ions in solution. Therefore, Acids increase the concentration of hydrogen ions in solution, and bases decrease the concentration of hydrogen ions in solution. The measure of the hydrogen ion concentration in a solution is called its pH. The pH scale ranges from 0 to 14. A pH of 7 is considered neutral, as the substance does not increase hydrogen or hydroxide ions. A pH of less than 7 is acidic, and a pH of greater than 7 is basic. Oven cleaner, ammonia, and baking soda are basic. Human blood is nearly neutral. Urine, beer, and battery acid are acidic. Usually, the amount of hydrogen ions in a solution is very small. For example, the concentration of hydrogen ions in beer is 10 to the minus 3 moles per liter, which is only 0.001 moles per liter. Each reduction of pH by 1 unit represents a 10-fold increase in the amount of hydrogen ions. So a solution with a pH of 2 is 10 times more acidic than a solution with a pH of 3.